Welcome to day 2 in the journey of mastering LLMs in 30 days. In an NLP pipeline, the first step is to process the text as an input which is suitable to the model. With LLMs in the picture, we don't do a lot of text cleaning as we discussed in the prerequisite video itself, but the most important step which we do is tokenization. Today's agenda is to know about tokenization in detail, where we'll be seeing what are the types of the tokenizers which are there, and then we'll go in detail about one tokenizer, which is BPE tokenizer. Let's start with a detailed introduction to the tokenization, asking the questions what, when, why, and how. What is tokenization? Tokenization is the process of breaking down a text into a smaller unit which is known as token. So these texts, like it can be a word, it can be character, it can be subword, or else whatever entity at you want to split a text, that also can be considered as a token. Let's say you want to split it as 2 to 3 characters together. So if you want to call it as characters, you can call it that. If you're calling it as subword, you can call it that as well, right? So yeah, it is depending on what type of tokenization method you are using. Tokenization is a very fundamental step. Like I said, it is a very important step in NLP and it is crucial for any NLP task. So that is tokenization. So if you are considering word level tokenization, right? If you see all of these words in the sentence, if you see it as a separate entity together, like for example, tokenization is the process of breaking down. That is tokenization, as simple as that. Now you might wonder, yes, this sounds very simple. So why are we making an extensive day, like, a whole day for this specific concept? You'll know that by the end of this video. When should we use tokenization? Tokenization is usually done once you feel that your raw text data is clean, and then you are ready for providing a model input, which will be tokenization process. Because the model expects numbers and you'll convert these text to numbers in the stage vector creation, which is embedding stage. Okay. So you'll do tokenization after text cleaning, but before vectorization. Nowadays, vectorization are part of the model itself because model itself have embedding layers, but you should do it once you feel like your data is processed in a common format. This text cleaning can also be seen as text formatting or processing, because it is not always possible that you will get your data in your expected format. If you format that, then your data is ready for training and then you'll provide it to your tokenizer. Why should you do tokenization? First, NLP models require discrete inputs, which is just numbers, so that it can convert into embeddings and then train itself. So for that, you need it. Granularity level. That is very important because the type of tokenization controls the granularity level in which the model works. For example, we made a character level story generation RNN. Possibly that could have been better if we trained it at word level, right? So yeah, that is provided in granularity control. Vocabulary management. Vocabulary management, it is like the model's knowledge of words, the collection of words that the model knows. That is vocabulary. This tokenizer will help you to create and manage vocabulary for language models. Let's say if I ask you a question of how many words you know, you will list down a number of words, and I'm sure the number of words you will list down will be more than what an AI can list down, because you know it as direct words. But if you increase that memory of your model, it will face an issue like you. For example, if I ask you about, like talking in a language, you will think of, like what is the next word? What is the next word? Like, is this the appropriate word? Right? So what like this vocabulary helps you with is it will provide a limited vocabulary for you to begin with, And then based on that vocabulary, it will have the capability to construct a sentence in such a way that that vocabulary is not that big. For example, if you know 50,000 words, you will know only 50,000 words. But LLMs, if it knows 50,000 words, it can construct 5 lakh words out of it, something like that. So that is vocabulary management. And we'll be creating those vocabularies with the help of tokenizers. And next is feature extraction. Like I said, LLMs take tokens as input, and those tokens are what is used to compute as embeddings and then provided as input. So that process is feature extraction, which will take tokens as inputs. Dimensionality reduction. By breaking down text into tokens, you can just reduce the dimensionality of your input. Now, how will you do tokenization? First, make sure that your text is normalized. Normalized as in not just, like simple normalization like this, text to lowercase, removing punctuation, handling special characters. These are old, okay? But these are the convention. But nowadays, you'll train it for some custom use cases. Make sure that your text is normalized for that use case. Okay, so normalized here also means that it follows a common format. Boundary detection. You want to identify where your token starts and ends. Simple things can be like simplifying it. As an example, could be here. Am I splitting at, space level, white space, the quick, brown, fox? That is white space level. You can do it at character level. Okay, it's at character level here. And then what you can do it as, for example, there is punctuation. You can split it as punctuation, or you can write your own common regex rules as well, which will be very complex in nature, but it is upon you. Okay, so make sure that you define your boundary detection. Next is to extract those tokens, where what you will do is you'll separate that tokens from the original text. Okay, just take those tokens which matches your rules, and then you'll process those tokens. For example, Subword tokenization is a tokenization which what it will do is it will be additive kind of tokenization. Okay, so here is an example: the quick brown fox jump space ##s. It means there is something which needs to be joined together with, so it is jump and then s together. Okay, jumps over the lazy dog. Like I said, for you, jump and jumps are 2 words, right, in your vocabulary. But for LLM, it is just 1 word along with a suffix. Okay, that is why I said LLMs are efficient than us in managing our vocabularies. So why do you need this tokenization? We already see that. But as a significance, it will provide language understanding. It will manage your vocabulary, like I said. Multilingual applications, for that you can use tokenization methods like BPE, because that will ensure that there is no unknown token in it. You'll handle rare words, like if there is even a rare word, for example, the longest word in the world, supercalifragil, something like that. There is a word like that, and then there is a disease name, which is ironically lung related disease, if I'm not wrong, and then that word is pretty huge. Okay, so if you want to represent that word as well with the help of LLMs, you can do that, because LLM will work at subword level. Okay, this subword level will break down that word in subword units, and then it will work from there. Okay, it will like proper tokenization will give better performance. It will make sure that the text is consistent, the tokens is consistent at a consistent level. Basically, it is very efficient, and then it will help you in feature engineering. Okay, these are the whys, in a different aspect as a significance. Now that we have an idea about tokenization, let's see about what are the tokenizers which are available. First, character tokenizer. A character tokenizer, as the name suggests, will break down text into individual character. So these characters will also include spaces, punctuation mark, everything will be a separate token. So here you can see hello world, HEELLO, comma, space, world, and then exclamatory mark. The simple advantages is it is very simple. You will never face out of vocabulary. Out of vocabulary is something like, it is an unknown word for the LLM, but unlike humans, it can't learn on the go, right? So it will always be unknown for it. So if you are not facing that issue, it is a very big plus point in your tokenization method. These are useful for tasks which involves character level analysis. But the disadvantage is that first, you lose the word level semantics. Each word will have its own advantage and disadvantage, right? Considering hello as HELLO and as hello, there is a difference, right? So that word level semantics is lost here. And then now, if I split it as hello world, the sequence has 2 tokens, but right now it has 5, 6, 7, 12, 13 tokens, which means it is going to be computationally expensive. And yeah, so since it is like this, it will not capture the language structure and all. Okay, but still, if you want to do this, all you need to do is just call the list of function and it will be done. Okay, so that is character level tokenizer. Let my kernel connect. Unless and until then, yeah, here you can see. Now, what is word level? If it is splitted as words, then it is word level. And here what we'll do is we usually split it as spaces, or else if you think like, for example, I want sentence level or like at some punctuations, you can also do that, but most common is white space level. So here you can see the quick brown, everything is separated here together. So you preserve word level semantics. It is easier to interpret. Now see, if I give this, right, would you prefer this kind of a text input or this kind of a text input? I think with longer sequence, everyone will say like this, right? So it is very easier to interpret and it will work very well for many NLP tasks. But the main problem comes into the picture, which is large vocabulary size, because each word should be there. If it is not there, you will have out of vocabulary words. So if you are going to manage that, you will increase your vocabulary. So if you increase your vocabulary, then it is going to be computationally expensive and your model won't be able to predict the next word very well. So if there is a compound word or unconventional spellings, like I said, the world's largest token, right, then your LLM will struggle there, even if it is there in the vocabulary, right? Because that is a very big token. If you want to do what you are word level tokenization, just call word tokenize from NLTK tokenization and then you will get your output. Okay, so this is word level tokenization. Like I said, word level can be anything, but white space is just splitting it at white space. Okay, and here if you see, the punctuations are not considered a separate token, but here punctuation are considered a separate token or a separate word. Here you can see dot is separate, right? So that is a very important difference between word level tokenization, common word level tokenization, and your white space tokenization. So this white space tokenization won't handle punctuation well because it is together maintained. And then here it is simple, fast. Again, whatever advantages are set for word level, it will apply to white space, and whatever disadvantages are set to word level, all of those will be applied for white space. So yeah, that is white space tokenization. Now coming on to the important type of tokenization which is performed nowadays, and in that important type we'll be seeing about one type in very detail, which is byte pair encoding. Okay, this falls under a tokenization method which is known as Subword tokenization. Subword tokenization is a method, as the name suggests, to break words also into meaningful units so that you will be balancing the vocabulary size, also the semantic representation. It is like getting the best out of both of character level and word level. It is like between the character level and word level, where if a word is it in its root form, right, it will obviously be there in the vocabulary. It should also be a very common word. Okay, but for example, if it is playing, playing, plays, played, if you are considering all of these to be a separate word, that is a problem. For example, let's take walk, walks, walking, walked. Let's take these three, and then plays, played, playing. Did you see a common pattern here? It is play as a common word, which has plays as s being suffix, played as suffix, td, playing, ing suffix. This is common in English, right? Subword works on that. What it will do is it will try to split the word itself into smaller words, making sure that the semantic representation and vocabulary size both are balanced together. So Subword tokenization, in this approach, you will handle out of vocabulary words. Mostly you will never face out of vocabulary words when you use methods like Byte Pair Encoding or Unigram. In WordPiece, there is a chance you might go into UNK tokens. Okay, but we'll see about these 4 tokenization methods right now. The first one being Byte Pair Encoding. So the Byte Pair Encoding is a method which starts with a vocabulary of initial characters, which is individual characters. And what we'll do is we'll go in an additive approach where we will merge the most frequent adjacent pair of characters. Don't worry about the sentence if it is very complicated for you. I'll explain it very simply. Let's say you have an initial vocabulary of individual characters. Okay. What you will do is you will count the frequency of character pairs in the corpus. For example, here it is hug 10 times, pug 5 times, pun 12 times, bun 4 times, hugs 5 times. Okay. So these are the words, and the base vocabulary is B, G, H, N, P, S, U. After one merge, how it will happen is if you see UG is together, UG here it's together a lot of times, UN is also together a lot of times, and apparently if you see hug itself is 10 times and then there is a suffix here. So even if I'm considering at first level, right, UG and UN will be a token which is combined together. Okay, here you can see that UG and UN. Instead of separating as HUG, UG as 3 tokens, you will split it as HUG, 2 tokens. What you will do is you will repeat these 2 steps, counting the frequency of character, which we did now, and then merging the most frequent pair and then adding to vocabulary again and again until your vocabulary size is reached, desired vocabulary size. Whatever issues we have addressed as main issues of tokenizer, everything will be solved here. Balance between vocabulary size and token semantics, and then handling rad words, out of vocabulary words. Subword semantics is captured here, works very well with multilingual models, but there are disadvantages as well. Sometimes the split wouldn't make any sense for some words, so it requires a training for corpus. But like the training would not be something like you'll expect that long and all. It is a very small training, and then at some point of time it will not capture the morphological structures effectively. So there is a variant of this tokenizer which is Byte-level BPE, where instead of working at these token level, it will be working on its byte level. Okay, so this is how that works actually. So you can see this is a separate token here, is a separate token. Sentence was, this is a sample sentence. Okay, here you can see this is 3, all of these 3 are common words. Okay, like you can say it as stop words and all, but sample, if you see, is separated as SAM. PLE for some reason is there in the vocabulary for some reason, I'm not sure. And sent and ends are together. Ends is a suffix, a very common suffix, so that is there. And then full stop is also there. Here you can see, like it is not splitted at character level, it is not splitted as word level, right? So yeah, that is BPE tokenizer for you all, and byte level BPE right now. Okay, next we have WordPiece. WordPiece is similar to BPE, but instead of choosing the most frequent pair, it will try to identify like which token has the maximum likelihood to be there in the training data. Okay, so this will be as similar as BPE, but it is very computationally expensive because it should see the training data a lot, and then it will say like this has a very high chance for occurring. But with this, there is a possibility for you to get UNK tokens. Okay, so the advantages and disadvantages are here. Again, the process is going to be similar. Instead of seeing the frequency in the vocabulary, in your vocabulary, initial vocabulary. From there, you'll see it as like, how likely it is there to be there in the training data. Here is a code to create a WordPiece tokenizer, which is similar to the code which is there for Byte Pair Encoding. But I'll explain this a bit. Okay, why I'm not explaining BPE tokenizer? Because we are going to create that tokenizer from scratch and also based on Hugging Face at the later end. So here you'll first call the tokenizer, saying that the type of tokenizer is WordPiece with my UNK token being UNK. UNK is unknown token. Okay, we are creating a trainer because this needs to be trained on a corpus, initial corpus, and for that you need to provide your vocab size, and the vocab size is 2000 here. Special tokens are UNK, unknown token, CLS classification token, separation token, path token, mask token, and all. What is the pre-tokenization level? Like I said, you want to split it at some level and then work from there, right? So for that, we are going to work at white space level. Now, once you create the tokenizer, you'll train it by calling the train function and tokenize it by just encoding and then providing the tokens. Okay. Let's see how WordPiece does the same task. You can see this is what I like in WordPiece. If you ask me personally, I'm a very big fan of WordPiece tokenization more than Byte-level BPE. But the only thing is the likelihood of an unknown token being occurring is higher with WordPiece tokenization, but still it can be handled by providing all the character set when it comes to multilingual languages. And when it comes to multilingual languages, it will increase the computation. If you are fine with that, with English, I think I'll always go for WordPiece tokenization any day over BPE. That is my personal thing, because here you can see this is that is fine. Yes, it is saying A is a part of the previous word, MP is a part of the previous word, LE is part of the previous word, which means LE will be MPLE now, and then MPLE will become AMPLE, ample. Let's say put it as sample, and then ample also says hash, so it will become sample. Okay. Then again, the same thing persists, sent and ends, right? So this is why I like WordPiece tokenization a lot, but it can be computationally very expensive than BPE. That is an issue with WordPiece. But yes, I like WordPiece a lot. WordPiece is used in BERT, DeFi, and even I think in some few LLMs which are coming right now, I think WordPiece is used. But most common LLMs which we see use byte pair encoding. And that to byte-level byte pair encoding, not normal byte pair. Okay. So as far as the Unigram tokenization, it will start with a large vocabulary and then it will remove tokens to reach the vocabulary. Till now it was additive, right? So you'll try to merge, but here it is, you'll define a bigger vocabulary and then you'll remove it. So first you'll create a large vocabulary, you'll have a loss function. We are not going to define it. Hugging Face would have done that. And you'll run this tokenizer on your current vocabulary, which is constructed over a corpus you provided, and the trainer will be there from the Hugging Face. Now what you will do is, for each symbol you will calculate a loss, and if it is like whichever, like for example each token is there a symbol, okay, for each symbol you'll calculate a loss if it is removed. Okay, so how much loss it is increased. We'll remove the percentage of symbol to attain the exact vocabulary size you want, finding the lowest loss increase. So here it will open up a lot of possibilities when it comes to multiple tokenization levels, because this is a format, right? So it will be very robust in nature. It is very optimal to find the vocabulary, because you are working down, okay, from above you are coming below, which means your vocabulary is good, but you are removing the tokens which has very less possibility to be there in the real world. Okay, and the disadvantage is that it is very complex to implement compared to BPE and WordPiece, and also training will be harder. But for us, nothing. Okay, same code, nothing is changed. Okay, we are providing the same corpus here, and if I provide it, it is gonna say T as a separate one, HI as a separate one, S as a separate one is like, this is doing it in its own way. But yeah, Unigram is also a very good method. Okay. And then finally, SentencePiece. SentencePiece is not a tokenization algorithm by itself. It is a framework where you can use BPE or Unigram. So what it will do is it will have input as a raw stream, where space is also considered to be a part of the token set. Treat the input text as a raw stream of characters. Characters means 111, okay, including spaces. You'll apply BPE or Unigram there, and then what you will do is you will learn the vocabulary that includes a space separated token. So here you can see hello and then space, and then world. So it is two things. When you do it in this kind of a coding method, right, this is logic. You can reverse it easily, and then it will be very consistent. You are setting up boundaries, so it will be that also will be very well. But at times it will not be as good as the other methods, because you are doing a higher level on top of something, and that is always not good. Okay, that is why SentencePiece is not used a lot. Okay, so now we saw about all these methods, and if you are going to use for a general purpose model, GPT is good. If you want to work it with encoder models, basically when morphology is the most important thing, right? Like you need to understand better. Encoding is very important. Then you go for WordPiece. And other two methods, it is basically if you want multilingual, go for SentencePiece. And Unigram is working on top of anything, it is just to handle ambiguity. But we are going to focus, as the example I've already provided here, it is to focus on BPE. So I have created a document here for BPE. Let's see about how that works. First, what is byte pair encoding? Originally, first byte pair encoding was a data compression method where the most frequent bytes will be replaced with a single byte. Okay. In NLP, this has been adapted to merge the most frequent characters. Here, instead of bytes, it will merge the characters. Now you will know that how byte-level BPE happens actually. Pre-tokenization, what it will do is it will split the word by spaces, and once it is done, it will add a special symbol underscore to say this is the boundary of the word, and here the boundary is space. For example, low, lower, 9, newest, widest. Here it is becoming low underscore, lower underscore, newest underscore, widest underscore, because these four are the unique tokens which are there in this text, and the occurrence time is given here. Okay, now you have the list of words and the frequencies and of which that words happens, or else you want to call it as tokens. That is also pretty good. So the number of tokens are already, number of times the token has appeared is also there. Then you are ready to implement BPE. First, you'll create a base vocabulary. This is how you'll construct a vocabulary with the tokenizer, because tokenizer is focused on creating a vocabulary, because while inference, what you will do is you'll try to see the word which is there in the vocabulary, and then you'll split from there. Okay, that is how you'll do. So vocabulary construction is all about what a tokenizer does. So first you will take the base vocabulary, which is character level, LOWERNEST WI. Okay, so all of these are there, and then underscore. Now what we'll do is we'll represent these words in base vocabulary, LO underscore, W underscore, LO, WER underscore, and so on and so forth. The third step is merging the most frequent pair. First is creating a base vocabulary, which is just characters, and then unique characters, all the unique characters, and then representing these words as characters, and then merging the most frequent pair which occurs in these characters. For example, here you can see newest, widest. Here it will happen at level, n-gram level. If you want to see two characters repeating together, it is bigram level. If it is 3 level, it is trigram level. Okay, so yeah, first if you start it as bigram level, it is going to be ES together, and it will be combined because it occurs 6 times in newest. Here you can see newest is 6 times, widest is 3 times, so ES has occurred 9 times. Now these words will become NEW ES underscore T. If you see ES and T itself, it's occurring 9 times, so it will become NEW EST EST. Here EST and then underscore are there together. You can also do it as T underscore, but T underscore is not something we see commonly, is what is the assumption here. Okay, this is just an example working of how BPE basically works behind while it is trying to construct the vocabulary. Okay, so it is becoming NEW EST underscore WID EST underscore. Here in lower, what will happen is, if you see yellow will be merging it as low, and then if you see W is coming up together here our assumption is that the vocabulary is this much only. Okay, that's why it is very important that you have a wide range of vocabulary while you're training your tokenizer. Okay, so low will be a separate token already, and then lower also. Okay, but you will not merge low and underscore here because it has occurred only one time, and in lower it is not there. So what you will do is you will stop this merging process. This is repetition process. Okay, you'll stop that when you feel that the vocabulary size you want is achieved. Okay, here are the merge rules, and here now this is your vocabulary. Okay, this is your vocabulary, and if I give a new text, what you'll do is first put it as words, add an underscore, and then break it into characters, which is there already here. For example, the words are newest, binded, and lowest. Okay, so before going here, I would like you all to just work it out. Like, you have seen the rules here already. Based on those rules, try to tokenize this. I hope you would have done that. Yes, now we'll see how it happens. Here, first we'll combine this ES in newest. So that will be ES and T. Like, ES first will convert E and S to ES, ES and T to EST, and then EST underscore to EST underscore. So it will be EST underscore NEW EST underscore. That is our final token. When it comes to binded, we don't have any rules which is applicable here. So it will be BINDED. But when it comes to lowers, we already have a rule LO being low, and then LO and W being LOW. Here you can see everything is bigram level. Okay, so LOW ERS. So if any token which is not there in the vocabulary, it will be replaced with UNK token, and that is why what people do is when they work with Byte-level BPE or BPE, they'll just provide the character set of any language they work with. Okay, so that at least at character level, that will be tokenized and there will not be any UNK there. Okay, so the tokenization result is already here. Here you can see find it as UNK because none of these values are already there in our vocabulary. Yes, except N. So it will become UNK. Okay, because that whole word should be represented somehow. But there are some things, for example, I is not there, B is not there. But yeah, N and D is there. I think D is also not there. Yeah, D is also not there. N and E only is there. So you can't represent that token. So it will become a UNK token. Okay. So this is how basically byte pair encoding works. Now, how will byte level BPE work? Instead of working at character or word level, it will operate at byte level. What it will do is it will convert the words or tokens to raw bytes as like a numerical representation of characters in the computer, similar to your ASCII coding. And this allows to handle all the Unicode characters. Like if you see ChatGPT and all, right, it can generate emojis very easily because these work at Unicode character level. Okay, it works at Unicode character level only. The byte level BPE ensures that any character can be encoded regardless of what kind of encoding it is, like UTF-8. So this will be very useful if you use for multilingual languages, especially like which has unique characters like Tamil, Chinese, Arabic, Hindi, and so on and so forth, where you see a possibility for a lot of unseen symbols coming up your way with lots of edge cases. There, byte level BPE will be very useful. Why does GPT use byte level BPE? GPT models will work with vast languages, which will have emojis, like, world level people are using it. You won't know what kind of symbol or what kind of token is going to be coming your way. But when you work it at byte level, that will allow you to, have the tokenization process almost being lossless, which means like, UNK token is not there and you are tokenizing it correctly, which means it is lossless because you are not losing any information. How this byte level BPE works. First, you'll convert the text into a byte sequence in its UTF-8 encoding. This is under the impression that, like I said, you can use any encoding. This is under the idea that BPE occurs at UTF-8 encoding. Okay. A is 97, P is 112, P again 112, L 108, so E is 101. So it will be like this. Okay. So you will apply the same processes like you applied for byte level for for normal BPE to byte level BPE as well. And here you can see it is T underscore PP, where it is saying like, it has occurred 2 times here. So that is why the merge is there. 97 T underscore PP 108 101. Okay. If you do it as tokenization, what it will do is it will be saying like, app and then LE, because the occurrence of A together with PP is very high. And it will also handle characters very much, because instead of character like emoji, you will be providing this UTF-8 number. So that is very easy for the model, right? So the final tokenization will be byte values will then be like, again decoded. First, what you will do is you'll break down the text into byte sequences, and then you will merge the frequent bytes to generate the token. That is how byte level BPE work. Just consider that instead of working at character or token level, you'll work it at byte level. That's all is byte level BPE. But the benefits is, like I said, like, universal coverage, efficient representation, like, you can represent any number of words with that, and you will not lose any information. Okay, this is how GPT model works. For example, GPT-3. Okay, let's consider that, and then along with the emoji. Here you can see everything is encoded here. So what it will do is, after number of merging together, GPT and Amazing will become a single token. Okay, and then Rocket emoji will be another token, Yeast will be another token. Okay, that is how this works. If you remember, or if you don't know, like I'm just saying, GPT models use an encoder which is tick token encoder, and tick token encoder is what tick token encoder use this kind of tokenization method as its base behind. Okay, so yeah, that is how byte level BPE works. I hope you understood how byte level BPE works, because if you are using a tokenizer, it is very important that you understand it so that you will know your model's flaws. Okay, models' important flaws can be understood with the help of tokenization. If you tokenize it well, you will get very good results with your LLMs. Okay, now let's see how you can create that kind of a tokenizer from scratch, BPE tokenizer from scratch. I'll just walk you through these codes. Okay, I have provided it with detailed doc strings, so you will be able to understand how things works by yourself as well. Okay, so first, from BPE tokenizer scratch, I'm creating the BPE tokenizer, and then OS is there. I'm providing my corpus file path, and then tokenizer, like, how I want to save it, like, where do I want to save it. So the training tokenizer, what it will do is it will take the corpus, it will initialize the instance of tokenizer, it will train it and save it. At runtime, you'll create an instance of the tokenizer, you'll load your tokenization file, you'll encode it. Okay, this is all there in this train file. The important file is this one, creating the tokenizer. Okay, so for that, first you need to see what is the base tokenizer. Okay, so here these are functions which we will override. Right now it will be not implemented. Okay, train, encode, decode and all, but you can build a vocabulary. Okay, the byte level tokens, it is 0 to 255. Okay, so what you will do is you'll just provide 1:2:3:2. That is a dictionary. of integers which are mapped to each byte. Okay, that will be a vocabulary which is being constructed here. For each byte, you will create a single byte token, and for each merge token, those will be together as one token. If you're working as bigram, it will be two merge token. We are working at bigram here, and that two token will have one number in the vocabulary. Okay, so that is building a vocabulary function. And how that will do is, it is assumed that you have merges ready. Okay, self.merges, it will be an empty dictionary. You need to merge that, right? So once your merge is done, it is just creating an empty dictionary from and to you can map it. You have to map your bytes basically. Okay, so how will you save it? You can just open and save your dictionary as anything like you want. Okay, you can save it as a normal file, or you can just add an extension known as vocab and then save all of these. But make sure that you decode your bytes, because if you are providing it as bytes, no one is able to understand that, right? No one is going to be understanding that. So just write it as bytes. Okay, so these are all just like writing a format in which you can see it and understand it. Okay, so this is to load your vocabulary. Okay, so what you will do is you'll go through each of those lines and you'll split it as space level, because so you can see it is split as space level, ID and token. Okay, so that is how you work here. You'll read your merges, and then based on those merges, you will build your vocabulary. Okay, so I'm just giving you a walkthrough. I'm not going in detail because we already saw the in detail working previously. These are just basic level things. In BPE Tokenizer Scratch, what we are going to do is encode, decode. First, we are going to see about the train function. Okay, which takes three arguments. Yes, text, where it is the input text you want to train on, basically your corpus. Vocab size, like what kind of number of vocabulary size you want. Verbose, do you want to see but debugging and all. Okay, return, this will return nothing. Instead, what it will do is it will change the merges and vocab attributes, self.merges and self.vocab. Okay, so how it will do, it will convert the input string into byte level integers, and then it will iteratively merge together the consecutive byte pair until the vocab size is reached. And each time a pair is merged, a new token is created, and then it will be assigned the next available ID, because your 0 to 256 already is done. Okay, from 257 you'll be adding it. That's why I said it is additive. Okay, you need to merge in such a way that, for example, if it is 300, it is going to be 44 new tokens are to be created. So that is what we are doing here. We are making sure that our vocabulary is greater than 256. Okay, and the number of merges you need to do is just subtracting that vocab size from 256. Okay, first what we'll do is we'll get the bytes of text, and then we'll consider byte sequence is first obtained here, and that byte sequence is separated at character level with the help of list function. Okay, so what you will do now is, for the number of level of merges, first we'll use get stats function. These are all there in the utils. Okay, so let me open the utils file here. You can see get stats. What it will do is, for example, you have IDs 1 2 3 1 2. It will generate pairs like 1 2 2 3 3 1 1 2, and then it will find the occurrence 1 2 has occurred twice here, and 2 3 occurs once, 3 1 occurs once. Okay, that kind of thing. For example, your collection.counter you have seen in Python, right? That kind of a function is what get stats does. And that stats, if you get the max, right, which is the most frequent pair, that is what is the pair here, that will be added to the merges and then added to the vocabulary as well. Okay, you'll get the ID of those and then it will be added. Okay, so if it is verbose, we'll print the merge as well. And now the self.merges is updated, and this process will be repeated for the number of merges. Okay, given a new sentence, let's say your tokenizer is trained, how you will compute the tokens at inference time is, you will again calculate the bytes, do it at a list, And what you will do is you'll make sure that it is greater than 2, because for you to perform even one merge, you need 2 tokens, because we are working at bigram level, right? You will get the stats, and then you will see the best pair to merge, which has the lowest merge index. Okay, that is how you can go additive. First to, for example, EST, right? First you need to find if there is ES together, and then ES and T. That is why it is first min and then combination. Okay, so if there is no valid merges, you'll just break the loop and then say these are the characters, and character level you are gonna work. But if it is there, you'll just merge and then return the IDs. Decoding is just referring the vocabulary. Okay, so this is how BPE tokenizer is created. I know I've just run through it, but it is very simple. If you remember all of those concepts I said, you can understand this. And I have an exercise for you all, because what I need you all to do is, I need you all to try to understand this code, and also try to understand the concepts which I have discussed today, and then see if you can create a vocabulary by yourself with the help of BPE tokenizer, which you created by yourself. Okay, let's see if someone is able to do that. You can refer this, but there are some flaws in this code which I know, and I kept it on purpose. I want you all to face multiple scenarios. I'll just give some conditions. Okay, there should not be an occurrence for unknown token. Okay, let's say I will work with 5 languages. Okay, let's say I'll take English, German, French, Hindi, Tamil. Okay, let's say these are my 5 languages, and this is a challenge. Okay, you need to create a BPE tokenizer, Byte-level BPE tokenizer, where any token I give in these 5 languages, you should be able to do that. I'll soon create a Google form for submission, which will be provided in the link here in the description. The link will be provided in the description. You can make a submission there, and whoever does it best, yes, we'll see. We'll probably have some prize for them, probably a book for them. Okay, that is something which I can do. So yeah, but if you are gonna do this efficiently, you are not gonna train by yourself. Okay, rather what you are gonna do is you're gonna use Hugging Face. Okay, you'll call the pre-tokenizer byte level. Okay, and then the tokenizer is also BPE. First, you will take your training corpus. Load dataset will load a dataset from Hugging Face. We are just writing it as line level with we'll go through each row, write it in the file, and then add a /n token to add the next line in the next next row in the next line. Basically, we are taking just the 1000 samples here, and then we are trying to construct a tokenizer of vocab size 25,000. And by the way, the vocab size I want you all to work with is 10,000. Okay, so here the special token is end of text. Okay, that is something which is very common. It is to say the sequence is ended here. That is EOS token. So first what we'll do is we'll initialize the BPE trainer here with the vocab size and the special tokens, and we'll train the tokenizer, which is already initialized here with the trainer provided already on wiki text, which we constructed. Here you can see the wiki text. Okay, it is a pretty big corpus, but I don't want you all to just follow this alone. Probably you can build it on something else. Okay, probably we can make it as a 2-part challenge. I'll let you know the 2-part challenge at the end of this video. Okay, so now we'll train it from the iterator as well. It is just using a data loader. Okay, so you'll save the tokenizer by calling the save function. You'll provide a save path. For example, it is BPE tokenizer GPT here, which is already saved inside BPE tokenizer HF. I manually moved it there. Okay, if you want to load, just provide that path as load path, and then if you call the tokenizer class from file with the tokenizer file, you'll be able to load it. Okay, so here you can see this is how the tokenizer file will be. These are my tokens. Okay, if you see, I provided 25,000 there, and there will be 25,000 tokens here as well. 24,999, right? So when you want to encode text, just call encode, and when you want to decode text, just call decode. With encode, it will be text, and decode, it will be token IDs. And if you want to save it as Hugging Face Tokenizer, right? Just normal, not normal tokenizer, just as Hugging Face Tokenizer. Just say beginning of sequence and end of sequence. Maybe you can say like, end of text as beginning of text as well. Okay, it is upon your wish. Just provide BOS token and EOS token. EOS token providing as end of text is itself more than enough. Just wrap your tokenizer with that and then save as pre-trained tokenizer. That is what will create this one. Okay, here you have BOS token and EOS token are your special tokens, and this is your tokenization config. Here you can see your BOS token, EOS token, cleanup tokenization spaces is true. I didn't set up a model maximum, so it is like infinity basically. And then the tokenizer class is pre-trained tokenizer fast. Okay, and that is this is the vocabulary. Here you can see it will be under the name vocab. See here, vocab, right? So, and also here if you see, this is the character set I was saying about. First you will compute the character set, and then you will move on to other things. So right now, for example, this is about German and all, and then you'll combine it. Okay, so this G is about like, saying there is something previous to it. Now, if you want to run this class, you need to call the run pipeline. Okay, what it will do is it will first prepare the training corpus, train the tokenizer, save it, load it, encode this text, and then decode it, and then you will save it with transformers. Okay, let's run both of those. We'll train our tokenizer from scratch, as well as we'll do it with Hugging Face. I hope my terminal is visible for you all. First, I'll do it with Hugging Face. Okay. Yeah, so now it is running. It is starting the tokenization pipeline. Okay, here it is starting the tokenization pipeline. Now it will prepare the training corpus and then do on all of those. Here it is tokenizing the words, it is counting the pairs, it has computed the merges, like it is doing it again and again. And here when I said let's test this tokenizer, it became LET colon or apostrophe. Yes, apostrophe. Yes, test this Tokenizers. Okay, this is to say there was a space before that. That is why G is there before TO alone. Okay, so yeah, if I had said while inference that cleanup tokenization spaces is true, it would have said like, this would have been mapped like this. But yeah, it is working. Okay, so here if you see, BPE tokenizer HF is there, and then GPT is saved separately. Okay, so now we'll try to train it from scratch as well. BPE tokenizer scratch train.py. I think it is gonna be like this. Here you can see it happened at byte level, and yeah, here you can see the vocab. All right, so there is something here which we are not able to see, but if you want to see the merges, here you can see this is how it became merged. 258 and 99 became 296 token. Okay, first you initialize till 256, 255, 0 to 255, and then 32 and 116 token merged to became 256, like that. Okay, this is how it works at the behind the scenes. This is just for your understanding, but the better way would be to use Hugging Face. So yeah guys, this is a very extensive video I made on tokenization, that to BPE. I hope you all like this video. I hope you all find this informative. I would just like to request you all to just hit the like button, share it with your friends. If you haven't just subscribed to the channel, please hit the subscribe button. We are on an LLM learning journey. I'll see you all in the next video. Until then, let me know your thoughts in the comment section as well. Happy learning.